Right. Well, now we have something a little different for CCS. We are talking really about software rather than large hunks of iron. We don't have to do it all the time. And it's my great pleasure to introduce Brian Ford, Steve Hague, who not only founded NAG, but turned it from a humble academic project in a university into quite a thriving company, and did it in a very interesting way. I'll tell you about it. Brian Ford. You started speaking.
So we're very flexible people. We just a slight change in the running order. Let's switch this on. Can you hear me now?
Yep.
Right. Good. Okay. Well, welcome everyone. I'm Steve Hague, and this is Brian. And we call this the NAG Library, the continuing story. We're very pleased and honoured to have this opportunity to present this history, and thanks to the people, David and Roger Johnson, Alan Thompson and others. Brian is the founder director of NAG. He led the project since its inception in 1970 through incorporation as a limited company, and you'll hear much more about this during the course of the presentations, 1976, and then for seems at times the rest of our lives until Brian retired from, shall we say, full-time employment into the myth that's known as retirement. I think he's even busier now than he was. And I was the first full-time funded employee of NAG, joining Brian in 1971, became deputy director in 78, and primarily on the technical side of the company. So we're telling the story of NAG, the organisation, the project, focusing mainly on the NAG Library, but as you'll see, that wasn't and isn't our only product. But that's, I think, fair to say, the most famous and enduring product in the NAG range. And we want, amongst other things, to talk about the principle on which the library was built, and the emergence of something we call the NAG Library machine. And we invent phrases as we go along. We talk about the NAG Library engine and so on and so forth. So you will see, I think, an emerging sophistication in the way we did things as we understood them more. We're also going to talk on something that we call numerical software engineering. This isn't a phrase that is too widely bandied around or understood. You don't often see conferences with that title, but actually, as I think you'll learn, it's played a quite critical role in NAG's development. We'd also like to talk about NAG not strictly from a technical point of view, but in terms of the many people involved. There are at least two people in this room besides Brian and me, David and Richard Field. And there may be others elsewhere in the audience who, in David and Richard's case, have been very much involved, and Brian will be saying more about that later. So here's the contents. I'm going to give shortly a lightning tour of where all these presentations are going, and then Brian is going to talk about in effect, the centerpiece of our activity, which is the Numerical Algorithms Library, the NAG Library. I'll talk about numerical software engineering. Brian is then on next, talking about people and organisation, the many, many people who've been involved and contributed, and the organisational side, the structure, the constitution, and so forth. Next, I'll give you a quick rundown on how our products have evolved and the way in which we think they're evolving, and finally there'll be conclusions and discussion. Please feel free to interrupt if you want points of clarification, or if I'm not speaking loud enough. With Brian, it may be the opposite. So we have planned to have some time, a few minutes at least, at the end of each segment of the presentation for questions, and if things go according to plan, there should be time for some discussion at the end. But do feel free to ask for clarification if what we're describing is unclear. Okay, so these green slides are way markers. They're to guide you through how far we've got in the afternoon, basically. So when you see one of these, this is hopefully will allow you to get your bearings in where we are. And I'm now going to give you a very quick rundown on the history of NAG and the NAG Library in 2 minutes, so that you have a sense of direction and distance in terms of where we're going. And then in the subsequent presentations, you should see the flesh emerging around this lightning talk. Okay, so, oops. NAG was formed as a collaborative academic project in 1970, with Brian as the initiator, and it had an aim of developing an algorithms library for a particular mainframe, which was one of the leading mainframes at the time. The founding sites were these 5 universities plus Atlas, the Atlas Computing Laboratory near Didcot. And what they had in common was that they were all getting, or had got, this then top-of-the-range system. I'm sure many of you know much more about that, or at least as much as I did. And the driving motivation, as you'll discover, was that basically the available software, the numerical software, particularly from the manufacturer, was virtually non-existent. So that was the driving common motivation. And the first release of what was then the NAG Library, actually it was the Algol 60 library, not Fortran in those days, but more about that later. And this activity gelled. It succeeded in producing a number of further marks or major additions in subsequent years, and you'll hear more about that. The people who worked on this came primarily from these participating sites, Birmingham, Leeds, Manchester, Oxford, and so on. And essentially all of them on a voluntary basis, and they worked with a small number of funded staff. I was one of them, who originally were based in Nottingham and then moved to Oxford in 1973. The activity gathered some pace, some momentum, it attracted some interest, and this led to 2 developments in the early to mid-70s. The first is that people with different ICL machines and non-ICL machines were very envious, or perhaps that's not quite the right word, were keen to get involved too. And this led to a kind of new NAG industry, which was porting numerical software to a variety of different machine ranges. And that, in a sense, was our first great technological challenge, apart from the mathematical aspects. Indeed, the interest came not just from academia, it came from industry. I think Brian Phillips was mentioning. Right. That companies like Philips, Redhill, Marconi, and other large organizations, BT and so forth, grew interested in this library, wanted to start using it, and that led to the development of a commercial library service in around 1975. So that this commercial service could be developed, and with the usual considerations of liability, limited liability and so forth, NAG Limited as a company was formed in 1976. So it, as a company, is 32 years old. A not-for-profit company limited by guarantee, and that's the status we still have. And again, we'll fill in more of that as we go along. From a financial point of view, broadly speaking, we met the objective that the funding agency during the 1970s, the Computer Board, in which Richard and others, and David, are very much involved. The aim that was set from a financial point of view was to be financially self-sufficient in terms of the full-time staff by 1980, and essentially that objective was met. Okay, so even after incorporation, the principles of collaboration continued. There were some changes over time, but still there was, and indeed still is, a significant amount of voluntary effort put into NAG, and again, you'll learn more about that during the course of the afternoon. And these were working in conjunction with a growing body of NAG staff. So these were funded staff working specifically for NAG. Most of those staff were based, and still are based, in Oxford, and others are located in NAG offices near Chicago, Tokyo, and Garching, which is near Munich. Well, actually, yes. Yeah. Okay, Brian will fill in the details. But essentially, there was a core of NAG staff in those 4 offices. Now, I'm coalescing history here with a vengeance. I think it's fair to say that during the 1980s and for much of the 1990s, it could be characterized as a period of steady growth in NAG activity, in our financial turnover, expansion of the product range, increases in staffing complement. And one particular facet of that very active period, one might say a somewhat heady period, because the world of computing seemed to be forever expanding, you might say. We were very active in national, transatlantic, European-funded R&D projects, amongst other things. And this growth reached a kind of high watermark in the 1995-96, of a turnover of just under £8 million. And at that point, the worldwide staff headcount was approaching 130 staff. Again, just to give you this quick overview and coalescing many issues into a single bullet point, it's fair to say that for one reason or another, market conditions worsened in the late 1990s, early 2000s, and led to some belt tightening and some refocusing on our library-related products and services based on those products. And again, we'll say more about that during the course of the afternoon. The really difficult thing when you engage in belt tightening is not so much in reducing costs, it's actually retaining a vision of the future, that you need to have a sense of direction and innovation. And I think we've succeeded in doing that. And I think it's fair to say the company now faces its future with renewed, restored confidence, profitability restored. Our turnover in the last financial year is approaching 6 million, and staff numbers are now back to about 70. So we are indeed talking about the history of NAG today, but also looking forward to, shall we say, a continuing history. Okay. So that's the lightning tour, and next Brian is going to talk about the centerpiece of all that activity, the Numerical Algorithms Library.
Well, the desire to build a general purpose numerical algorithms library is not a wish most people are born with. And to do it at least twice is even more unusual. But numerical algorithms libraries have taken up much of my life, and I actually don't regret it. The driving force has been the development of software for software solvers to enable scientists, engineers to solve their problems, and invariably expressed as equations in some area of numerical maths or statistics. And at the outset, the aim was to build a quality facility, and what quality means will become clear. And the library collection would be carefully selected to meet the needs of its users over the whole field of numerical mathematics and statistics. So in the late 60s and early 70s, we asked our university computing users what numerical areas they needed solvers for, and then set out to discover what numerical subject areas had reasonable and useful algorithms available. And so from the beginning, we were choosing the best, not simply taking what was available. And everyone thought we were being idealistic, but agreed to try and to help. Well, what was achieved? The NAG Library was built, much science and engineering was completed. We know of at least 30 Nobel Prizes won using the NAG Library. There was a tremendous stimulation of numerical analysis and computational statistics, with many new algorithms invented, and hence, I guess, the invitation to give this presentation for your society meeting. And can I join Steve in saying thank you for inviting us. Today for me has been a coming home. I solved equations using hand machines, Brunsvigas, in afternoon practicals as part of my maths degree in 1959 to 1962 at Imperial College, over the road there in the Huxley building. The looks of it, I wasn't alone in that. I actually preferred quantum mechanics to numerical mathematics, but that would be another story. However, I became involved with numerical software for the first time in 1967. I read the seminal paper by Francis on something called the QR algorithm and started a software implementation of it. And I was offered a joint post between maths, teaching quantum mechanics, and the computing centre at Nottingham University, and set up a numerical advisory service there for the whole university in the computing half of the post. Now, our computer was a KDF-9. Its design was based on Pilot Ace. We'll have a picture of that a little later, which was of course the brainchild of Alan Turing, and was built at NPL by Turing and then by Jim Wilkinson and colleagues. And the KDF-9 was a wonderful machine, 48-bit word, hardware double precision in the product, and true rounding. Now, even in those early days, our computing resources were saturated and had to be strictly rationed. So looking to improve the use of the facilities through the use of better numerical mathematics, I invited Jim Wilkinson and Leslie Fox to come and lecture to our users at Nottingham. And to me then, they were the absolute gods of numerical computing. Jim had just published the algebraic eigenvalue problem in 1965. He gave us 2 wonderful lectures. And during the visit, I showed Jim my QR. He said, "Do you want the good news or the bad news?" I said, "I'll take the good news." He said, "Well, it's not bad." I said, "What's the bad news then?" He said, "Well, I'm publishing my QR with Christian Reinsch in Numerische Mathematik next week." Leslie Fox, of sporting fame and numerical mathematics in general, sent David Mayers to lecture to us in Nottingham. David gave us 2 excellent lectures. He also had approximately 150 people for each of his lectures. These were amazing times. I built a numerical algorithms library for the KDF-9. I got good numerical linear algebra and random number generators, rather spotty coverage in nonlinear optimization, quadrature and ordinary differential equations, and 1 curve and surface fitting routine. I got some of the stuff from NPL and the nonlinear optimization from the group at Harwell, and I wrote some myself, including this infamous curve fitting routine. Did some serious testing and prepared my first body of user documentation. The take-up of the material was instantaneous by tens of people. I've never been so more popular before or since. Everywhere I went, I was stopped by people asking for specific solvers. for their particular research problems. And the many I couldn't handle, I fed as queries to NPL, Harwell and Manchester. Now, a number of other universities had KDF9s too, and they also had active numerical analysis groups. And so, for example, Linda Hayes worked with Fox and ran the user advisory desk in Oxford, and Adrian and Shirley were in Leeds. Shirley Little was doing a PhD in nonlinear optimization with Roger Fletcher. But none of them had developed numerical libraries. Each of them had a subject library. Well, then came November 1969, and we had the announcement of the 6A for Nottingham, along with these other famous universities. And this machine was so powerful that 30% of its resource could be given over to the operating system, dear old George III. Eric asked for a 6A library from me for Nottingham, for the reasons that Steve's already given. I wasn't interested. You know, I'd done one library. I wanted to do something else now. Eric said to me, Brian, you should do it. They need it. You know they need it. Well, I was lying in the bath. Notice the northern A. I was lying in the bath in Bunny in February 1970, and the obvious solution came to me. Build the library collaboratively. So I set about preparing a meeting for Nottingham, which was convened on the 13th of May 1970. And Linda and Shirley and Joan and Bart came, and we agreed we needed a quality library, developed collaboratively. And we agreed to build it in Algol 60 and Fortran for the ICL 1906A. We had resources in our centre which we could use. Each of us was strong-minded, hard-working people. We led from the front, and we individually did it ourselves. And at that first meeting, which is recorded here, we agreed certain things. That the base of the library was algorithms, individually selected and coded in both languages. The user documentation was as important as the software. There'd be an example program to show how each routine ran properly. There'd be a stringent test set for each routine to establish its correct functioning and to establish why it had been selected. And also, if an error was found in the software or documentation, we'd tell the users straight away, and also set about, obviously, correcting it. Now, the spectrum of users we had was very large. And formally, each had an equal demand on their resources. So everything had to be designed to cover their range of ability, requirement, and demand. Clearly, each user had a mathematical problem, to solve which would fit into one of the classifications of numerical mathematics or statistics that we chose. Most users were familiar with the vocabulary and language of their research area, but many of them needed support with the vocabulary and language of the mathematics of their study. And just an illustration, there's a man called Peter Mansfield in physics. He worked in nuclear magnetic imaging. First time I met him, he came to the desk and said, "You're a liar. Von Neumann says the algebraic eigenvalue problem can't be solved." I said, "Here's the solution." So he became a believer, decided to use the stuff. Then he goes off to Tokyo to give a lecture, gets a PhD student to come and get his results, just turned off the KDF9 at this point. And I said to the student, "Now look at the output before he uses it." Mansfield didn't. For an audience of 1,000 in Tokyo, he's put up on the screen, matrix numerically unstable, results totally unreliable. He was still seething when he got back to Nottingham. Give him his due. When he got his Nobel Prize 3 years ago for the nuclear magnetic imaging, he actually was good enough to send me an email reminding me of those days and saying thank you. And this is not untypical. A major factor in all of our work was the user documentation and making sure we kept their needs before us all the time. The selection of algorithms for inclusion had to satisfy user needs. And so we sought from the outset to establish an interaction between the users on the one hand and the algorithm developers on the other. Now, previously, users had simply gone cap in hand and gratefully received any algorithms they were given. What we sought to do was to identify users' actual needs and then get the numerical analysts to solve them. It was clear that the algorithms in numerical linear algebra would be required in many parts of the library, and that these also would be cross-called. At that first meeting, we had a philosophic discussion about the qualities, the characteristics of algorithms that we were looking for. And we came up with this list. Robustness was the ability of an algorithm to fail gracefully, delivering an error message. Usefulness was clearly too vague as a concept, and so at the next meeting we agreed this set here: stability first, robustness, accuracy, adaptability, speed. Speed was always last. There was far too much fast rubbish about. And later there's a wonderful confrontation between Christian Reich and Seymour Cray at Hague National Laboratory. Cray was talking about his Cray 1, and Christian got up and said, "Your machine, Seymour, is unsafe at any speed because of its dirty arithmetic." The reality was that some of our early selected algorithms had few or none of these properties, but the characteristics were a proper ideal, and the library contents would be updated in an ordered, notified, and consistent way. At the first meeting, we selected the first chapters for the library, and they're these. A few comments about them. Clearly, the linear algebra was fundamentally important. And some of our initial decisions were wrong. We stumbled badly over the statistics. I'll explain a little more about that in a moment. We actually included sorting as one of the priority areas, but it's not really numerical at all. Although, having said that, it's always been heavily used. Random numbers for simulation have always been vitally important. We failed to grasp the nettle of dealing with partial differential equations. And although it would have been very challenging, it set back the library the availability of such software for a number of years. The ODEs, as Joan Walsh never stopped telling me, were much more important than the initial list showed. Some areas were in the numerical infancy, and we just didn't have any software for them at all. And linear programming had been a package activity. We made it available as subroutines. That was a really good decision. Graphics and visualization, we didn't touch at all. It would have been too early probably, but it meant they were set back as well. So after some initial research, we recognized 4 categories of algorithmic coverage that was possible in the library. We had what we call general coverage, which things like the eigenvalue problem from day one. Ordered differential equations, which was sort of patchy. We covered most of it, but not all of it. Curve and surface fitting, spotty. Routine there, routine there, routine there, routine there. No general coverage at all. And then there's some areas that we weren't able to cover at all. Our aim, of course, was to move everything into the top category, and we've probably about achieved that now. It's probably taken that long to be able to get general coverage in a library of this kind for all the material we're discussing. So this is one of those signposts that Steve told you about. Marks of the library were released annually, and the additions to the library were cumulative. We had, Steve's got that gadget somewhere. I probably won't be able to use it, but never mind. There we go, it's 30. yes, I should be able to manage that. So we can see here that we had ordered differential equations right from the beginning, written by Joan Walsh. And there's my beautiful, ugly curvous surface fitting routine. For the nonlinear optimization, this was the work of Powell and his colleagues at Harwell, but they were great clumps of code, and we wanted the code to be modular. So the material was rewritten by Murray and Gill at NPL in the next 2 or 3 years thereafter. We chose to do the eigenvalue problem before we did the solution of linear equations, because actually in much of science and engineering, the eigenvalue problem turns out to be even more important. In terms of statistics, we had a very poor start. The reason being that we all sat down and agreed standards. And we agreed we'd all write the software to those standards. But the person doing the statistics said it was impossible. He'd agreed the standards, but he couldn't write code and documentation to it. And so basically, we refused to include the material in the early library, and it was only at Mark IV that we got a serious body of statistics, except, of course, for the random number generator. And the Neve generator was used for the first 4 years, and then Nick McLaren at Cambridge, a close friend of David's, if I may put you on it, David.
I have the last say.
I look forward to it. Nick wrote us a new set of generators. In the other areas, you can see we had here the approximation to special functions. This was a work of Laurie Schoenfelder, who learned how to generate the expansions required for portable algorithms for special functions. And we took the Abramovitz and Stegan as the standard by which to develop that. And as you can see, well, you can't actually, forgive me, but if you add those numbers up quickly, you'll see that after 4 years, we had 340 routines in the library. Just quickly looking at the chapter contents, the quadrature was a fascinating area. The experts in the UK in quadrature were O'Hara and Patterson at Queen's University Belfast, and we met twice a year throughout the Troubles in Belfast on the quadrature chapter. The amazing thing was that the only thing we could talk about was quadrature. We tried even talking about football, and it became an argument between the sectarian groups on the panel. We had what was then known as a Paisleyite, a member of the IRA, and everything in between. And they all knew, but they all worked in quadrature. Joan Walsh was the only numerical analyst in the founding group of NAG, and she did the work on ordinary differential equations. She'd had earlier code working on the machines in Manchester, but she was also able to bring together quite quickly a worldwide collaborative group. I'll say something about that in a moment. In fact, I should have stepped on these 2 slides. Because of my pathetic routine, Jeff Hayes and Maurice Cox were good enough to take on as contributors of the curve and surface chapter. One of the other interesting side effects of collaboration was that we had the simplex method of Nelder and Mead for nonlinear optimization. And because of that, we met John Nelder and started a long relationship with the inventors of modern statistics at Rothamsted, Fisher, Yates, Nelder, and Genstadt and related packages. I'll say something more about Jim in a moment. Linda and her colleagues translated the handbook routines in Algol 60 into Fortran, which was a fabulous effort. I've mentioned already, out of turn, the fact that the software we were offered for the statistics we couldn't accept because it wasn't up to quality, and it took us a long time to catch up in the statistics area in the library. The PO1 chapters was where we had our systematic error reporting for the library routines, and amazingly, the users really loved this. It meant they were getting warnings about what was going wrong with their calculations, and how they could therefore become more confident in their own work. But it also meant that they had to look at the documentation too. And I think you'll agree, documentation is the source that most people are not happy to turn to. So there was a twin benefit from that. Laurie, as I said, had this awesome responsibility of generating full machine accuracy approximations for the elementary functions and special functions we do. And then finally, we have the issue of the portability of numerical software. Well, we didn't know there was such a problem as portable numerical software. We just assumed, I think initially, there'd be no difficulty of that kind at all. But what we did do was address the issues of the portability of numerical software, recognize the issue and grasp it, studied machine characteristics and their parameterization in numerical software. I'll go into this more a little later. And so finally, a set of parameters were chosen for the library. So we're now looking at the library contents organization. Within each overall chapter, say for example, ordinary differential equations or nonlinear optimization, we were looking for subdivisions into different problem types. So that, for example, in linear algebra, we had first of all the eigenvalues and the nonlinear and the simultaneous equations. Then within each of them, we had real symmetric, real, Hermitian, and complex matrices. And we're able to choose algorithms to precisely address each topic and get the best for each. And that was possible with linear algebra. But in other areas, such as nonlinear optimization, these were only partially qualified. And so that, for example, we could go to unconstrained problems and constrained problems, and then within unconstrained problems, recognize four groups. A univariate problem, direct search, where all you could do was calculate the objective function, or a position where you had the ability to calculate the gradient vector of the objective function as well as the objective function, or the gradient function and the Hessian too. But that's as far as you could go. And what you wanted to do was to recognize these problem subsets so that you could choose algorithms to specifically address each. And that's something that we've constantly worked at. In building the library, we were fundamentally dependent on our individual chapter contributors. And clearly started with people that we had, but this soon changed. So that originally we had our colleagues at Oxford doing the linear algebra, with me acting as their validator. We dropped the BMD programs very early. We realized they've got nothing to do with libraries, and we clearly made a mistake there. And it was just wonderful to be working with people like Joan and Linda and Shirley. You look at the number of boxes there, which has just the name of a university computing centre in it. It meant originally they were totally responsible for the software in that specific area. Well, as the uptake and use of the library became clear, a series of chapter workshops were organised, from which individual chapter groups were formed and group leaders recognised. And each chapter contributor defined the substructure of their own chapter and selected the algorithm contents accordingly. Now, since each of them was now an expert numerical analyst, they knew the algorithms currently available in their own area. What was inadequate? Who was doing what to develop new algorithms in the subfields? And recognising also the holes that needed to be filled in. Remember, the contributors were and are voluntary and unpaid, and their interest in being involved was to drive the field forward, to broaden their own contacts and experience, and above all, to see their work being used. Wherever you went, you'd meet people who were contributors, and they'd say, how many uses do you think there have been of my algorithms in the last year? And we used to keep statistics so we could answer questions like that. And of course, from their perspective, most of them were academics, and they were interested in the reference and published use of their algorithms too. The linear algebra was crucial to the library activity. Oxford, as I said already, translated the numerical linear algebra from the handbook into Fortran, although the people at Argonne were doing that as well. Jim Wilkinson had provided all the Algol 60 copies of the software. Jim gave his blessing to the library project and committed to work with us. And Jim worked with us for the rest of his life. He appreciated the difference between numerical analysis, algorithm design, and software implementation. And this was really quite crucial. And he valued all three. He believed passionately in cooperation and collaboration. He urged us to be critical of mistakes in his own code. If you look at the handbook, there are all sorts of mistakes in the Algol 60 that's been published there. And we found that and corrected it. But we shared a philosophy of excellence for every phase of creating numerical software. Jim introduced me and hence NAG to the excellent group at Argonne, and hence the ISPAC and LINPAC activities, and to other people working in numerical linear algebra in the States and Europe. And the response of all of them was, well, if it's good enough for Jim, it's actually good enough for me. So we had the Linear Algebra Working Party, chaired by Jim, at his room at NPL from 1972 until his sad death in the early 80s. We're filling in holes in the numerical linear algebra offering, the inclusion and development of the Level 1, Level 2, Level 3 BLAs, input from the LINPAC project, which we're involved collaboratively too. We have the sparse matrix software from John Reed at Harwell, and we're updating the numerical linear algebra in the library constantly. And so Jim gave us his backward error analysis, his understanding of algorithm stability, the handbook with Reinsch, and also designed new linear algebra algorithms for use elsewhere in the library. And because he was always friendly and welcoming of the young, it meant people were always very glad to be working with us. Well, that was one chapter study. I've got to quickly flick through a couple of others. I've said too much about that first routine already. Jeff Hayes did a great job with Morris for us. And we picked up work by De Boer, as well as colleagues of his from NPL. Ian Gladwell validated the contributions from NPL in curve and surface fitting, and was described by one of our colleagues, Maurice Cox, as a very hard taskmaster. And they had some really fiery meetings and correspondence. At my retirement, Morris was good enough to say to Ian, or to all of us, but to Ian in particular, we were glad of his criticism, and the resulting code and documentation was much better because of it. But it took him 20 years to get to saying that. Joan did the ordinary differential equations. A great emphasis there on testing, and also some wonderful meetings. We had a meeting on boundary value problems in Manchester, and at it, Fox revealed his own dislike of computers. The reason he disliked them, he said, and why he would never use them, was because of the loss. There was always so much black box. There's so much loss of control. We also were able to arrange an outstanding meeting of people working in ordinary differential equations at Argonne, where Bill Gear, Alan Hindmarsh, Tom Hull, Fred Crow, Larry Champagne and Gordon. And they agreed a vocabulary that they would use in future for their testing regimes and also for identification of problem kinds. Nonlinear optimization, the main thing there, I need to move on, was it was the first chapter to recognize the need for easy-to-use routines in parallel with the full control routines. So library construction operation. We recognised the need for three sorts of software. Some users wanted black boxes which they could put numbers into and get answers out of. There are others who wanted much more control of their calculation at each step, and so wanted to operate using what we call primary routines. Underneath all of this, there were certain basic numerical utilities. Now, from the outset, preparation of the library and taking it through all its stages to its ultimate use by users was a substantial collaboration by tens and then quickly hundreds of people. Remember, the vast majority of those were working completely voluntarily without payment. And I called this process the NAG Library machine. You probably wouldn't guess where the name machine came from. It's Mayor Daley's machine in Chicago. The way he organised the wards there to run the city. But it is that idea of a coordinated human activity that is the NAG Library machine. Now, within weeks of actually distributing our first library, Manchester, who had a 7600 as well as a 1906A, were asking for a 7600 copy. And the well-known flower of Cambridge, sitting at the table here, was also keen to have a copy of the NAG Library on his IBM system. I think that's true.
Are you told that?
So we were immediately immersed in the twin problems of algorithmic and software portability. Recognizing and ultimately solving the issues of portability was one of the greatest achievements of our library project. It was a real contribution to science and technical computing. And as this slide shows, we also recognized the problems of computing language dialects and overcame those through using strict language subsets. And our aim was routines running to prescribe efficiency and accuracy on all the machines to which we took the library. And those routines were to be virtually unchanged. And what our contributors wished to do was to write a single routine which could be tailored for every computing configuration. So what we did is we defined a simple model of numerical and related features of any computer, relevant to the execution and performance of the software. And then we parameterized this model and then developed all the numerical software based on this simple model, so that the conceptual machine was described in terms of parameters. for example, the overflow threshold or the base of the floating point number representation, which clearly for an IBM 360 would have been 16, and for the CDC 7600 was 2. And hence the contributor designs his algorithm and writes the routine in the parameters of the conceptual machine. And then the algorithm and the routine are tailored for a particular machine by the choice of the values of the parameters. And the contributor then provides an implementation test for each routine to demonstrate that it's working correctly. We actually had numerical software portability wars in the early and middle 70s. One group wanted portability through the use of a single, commonly used and available, high-quality computing arithmetic. And the other group, which I was one of the leaders, wanted software portability so that users' programs could be easily moved between different configurations. And of course, both these groups were correct. So Cody and Kahan prepared the IEEE arithmetic standard. And we knew we'd succeeded when Kahan, the gentleman on the right, said to me in 1976, "Brian, we're all writing portable numerical software now." That was the big breakthrough. Now for a brief sermon on user documentation. Clearly, documentation is important to the software. Clearly, we were catering for different levels of users. And the documentation has to mirror the issues addressed by the software. So we wanted the evolution of the library. We wanted it to update stage by stage. And we needed portable documentation and information for portable software. And of course, we had to have the same chapter structure in the manual as for the library. So in the manual, it's document-based for ease of updating. And each chapter was headed by a chapter introduction with 4 distinct elements to fill in the background of the scientists and engineers about the mathematics that they were using. And then each routine, there was a document of 13 sections, and included in that was an example program with the input data and result for that routine. And the routine and the routine documents had the same name. Now, in its day, the manual was an international success. When it was about 12 volumes, it was growing great guns. When it got out to 16, then it began to lose some of its favour. But fortunately, by then, we were beginning to find ways of putting the documentation online. A critical facet of getting the quality of the library was the software testing. So the algorithm selection was absolutely crucial, but the software testing was equally crucial too. And in the first 4 phases of the NAG Library machine, each group, the contributors et al., validators, implementers, they all had their own test software. And the idea, of course, was that we had standards to which the material was written, but then test software that brought the library to its high quality and gave it its quality name. And clearly each contributor had his own independent test suite of algorithms for testing and selection. And of course each validator had his own set too. So it won't surprise you to know that if you took the stringent tests for the library, the amount of code there was greater than the code in the library itself. Also, the thing we generated, and Steve may say something about this, is that the automatic comparison of results was both an art and a science, because you couldn't hope to do it any other way. Algorithm testing. Well, again, Jim, God bless him, had set the standard for the activity with an error analysis of each algorithm included, with a detailed stability analysis too. and studying the effects of overflow and underflow. Indeed, he used these techniques for deciding on using householder transformations for the QL algorithm. And Brian Smith in IcePack used balanced backward error analysis techniques to check for algorithm portability and software consistency. The next phase was the validation. The thing we needed in validators was the strength to stand up to the contributors and tell them where they'd gone wrong. It wasn't a way to make friends. Library assembly. Well, this was at the point at which the software instantiation of a particular algorithm was thoroughly tested. And this is a truly grungy area of library building, which was and is vital for the achievement of quality. And this is where the diversity in algorithm design and software development within groups was straightened out and a unified style created. And of course, as far as possible, these standards were machine proven. Well, we developed a lot of sophisticated software tools for this activity, and Steve will be talking about that in a moment. Where implementation was concerned, already at Mark V, there were 44 different implementations of the Fortran library and 16 of the Algol 60 library. At Mark 21, which is the current version of the library in general use, there are 78 different implementations of the Fortran library and 39 of the equivalent C library. So there's a lot of software involved. So, conclusions, just 2 slides. The operational principles. We consulted our users. They defined what was put in the library. And the library machine encouraged people to consult with one another and learn from one another. Collaboration was the vital force which gave access to the required resources. At one point we had a discussion with IBM and again with the Department of Defence about whether they could build an equally competent and broad library. And they admitted they couldn't. They just couldn't bring the resources together that building a library of this kind required. But we were able to do it collaboratively. Clearly, coordination was vital. It meant that we had the individual chapters being developed. It meant the various phases of creation and distribution of the library were all planned and coordinated properly. Much activity could go on, and you could still achieve quality and standards. The planning of the individual chapter contents, etc., obvious. The standards, insisting on having as many as possible machine-based, and not accepting anything that didn't meet the standards you had. And of course, mechanising, which kept the costs down, and actually computers don't generally have Monday mornings in the way that some people do. Well, the conclusion of this part of the tour, the building of the library and similar library ventures led us to design scalable algorithms and develop portable numerical software. The issues of that, though, are still being met as new machines are created. And Steve will talk about that in the current work that the NAG office is doing. Along with the IEEE arithmetic, visualization, and symbolic computing, we actually changed the scientific and technical world. Computing, computational physics, computational chemistry, all of those came into being. And the great work in ecology, work in the finance markets, perhaps I shouldn't mention those, medicine, that much more constructive. All of these were possible because of this work. Underneath it all was the numerical mathematics, numerical analysis, numerical software, which we actually developed. So sums are important, chaps. Are there any questions? Or comments?
When did email come in? Did you have, I mean...
Email came in for NAG in 1977. I was the second or third user of email in the UK. I thought I was the second after the people at UCL, but then I discovered the Queen got it quite early as well. So whether I'm before her or afterwards, I'm not sure.
This email was with Arthur,
That's right.
which
And I was
74.
Yeah.
Yeah.
Well, I was one of the first European users of it, I'm told by the people at Livermore and Argon. And I learned, for example, there's a famous TV soap about who shot somebody. That's helpful, isn't it? Anyway, let's grab that story. I can't remember the detail. Dallas, it was about Dallas.
Yes, who shot J.R.
And I actually knew the answer 24 hours before it was published in the UK. And if I'd known, I could have made a fortune, couldn't I? But email was, of great value, because one of the things we aren't able to do today is talk about our relationships with people in the States. We just don't have the time in the 2.5 hours. But the email was vital for that. And indeed, this morning, I actually had contact with somebody in New Mexico and someone else in Arizona, right back from the early days of NAG. And we still do. Marchuk gave us an earlier routine from Siberia, but he wasn't using email. Well, perhaps we'll press on then.
Yeah.
I'll hand over to Steve.
Okay. So, and now for something rather different, not very much related, but somewhat, I suppose, using Brian's term, this is the grungy side of library building. No, I don't mean that. But I think if you yourselves had tried to anticipate what we're going to talk about today, you might have thought about numerical analysis, numerical software. I don't know how many of you would have anticipated we were also talking about syntax analysis, syntax transformations, sort of semantic transformations, parse trees and so forth, which is all somewhat computer sciencey. And certainly we didn't anticipate in the outset of the NAG project that we would get involved in such sophistication in terms of software tools and related software management mechanisms. I mean, it's been a long learning journey for us all. So, and indeed the phrase necessity being the mother of invention is absolutely true in this case. So, what I'm going to talk about now is what I, for one, and I think others, found that it became an unexpectedly important discipline. We wouldn't claim that we uniquely invented numerical software engineering. I think there are many other groups, NPL, groups at Argon, but I think we can claim to be co-founders of this very pragmatic discipline. This is not a theoretical approach, it's not a particularly academic approach. The primary goal is not to publish papers, though indeed we published quite a few in the process. The primary goal was, as Brian said, to discover how to write a library that had longevity, had quality, had applicability. And what you're about to hear of is that learning process that we went through over a number of years, from the early 70s and indeed onwards for the next 30-some years. The learning is still going on because the challenge keeps changing. Okay. So, first, let me say a little bit more about what we mean by software tools in the numerical computational context. For some of you, you may be thoroughly familiar with this. For others, it may be somewhat more esoteric. So I just need to give you, for commonality's sake, some background here. So, what makes numerical software special, apart from the obvious preoccupation with mathematics and so forth? Well, I think in a sense it's inherent in the nature of mathematics, which is try to understand formulaically how entities relate to each other. And in particular in the numerical sphere, as Brian said, you seek to establish key properties such as accuracy, robustness, performance, and so on. And having done that, you're very loath to lose those properties. Could be this.
Yes.
Right. I'll use a more conventional way to time this, this presentation. Okay. Now, words like reuse, reusable software, come into vogue and come into fashion and go out of fashion. There are times when the European Commission, for example, discovers reusability and then throws millions, billions of echoes into a vast array of projects, out of which, you know, who knows what comes. It so happens that numerical software developers have really been focused on reuse of software from the outset. I think they knew it was a kind of economic necessity, that you only really got one chance to do things, and you really wanted to make maximum reuse, particularly if you'd worked very hard to establish key properties of the code in the first place. So, the term reuse in the numerical software context means using essentially the same basic algorithm in a number of different computational applications, whether it's quantum chemistry or some ecological study or whatever, you name it. A different application, but the same essential mathematics you want to keep reusing. Now, sometimes that reuse will lead to improvements. You may then have to backtrack and check that what you've changed still works as well in these previous environments, for sure. Porting, or implementation, as we tend to call it in NAG, has a slightly different focus. That says, I want to be able to use this same software that I believe to be reliable, fast, whatever, in different computational environments. And in the numerical sense, a computing environment consists not just of a host computer, but typically of a compiler, because compilers can do wretched things to your program, compiler libraries, arithmetic processes, arithmetic modes, and so on. So these two key issues of reuse and portability actually, as Brian said, we came to learn how important they were and then spent the next 30 odd years working out how to handle them. So a software tool is any piece of software design intended to assist in some way in whatever phase, the various phases of numerical software. Programming aids, mechanical aids, call them what you will. They fall, in our context, essentially into two categories. Those that analyze, so you might want to verify that the code you've been presented by a contributor conforms to your version, your NAG Fortran, shall we say, for the sake of argument. You may want to compare two bodies of code. This code has been had this history, that code has had that history. You knew they have a common ancestor, but how do they actually relate now? Common problems for any of you who manage large bodies of software. But the key thing is that they don't transform the program. They essentially report on the programs as are. Transformers are in that sense inherently more dangerous. They're surgical. They actually intervene in a program. Precision changes, standardism enforcers, interface generators, and so forth into language converters. And I'll mention more as we go along. So, two basic questions. Why did a numerical analysis activity, numerical software project, get involved with all these tools? It wasn't, as I said, really anticipated at the outset. It really was through necessity. And why is analysis and manipulation necessary? And if so, and then, if it is, why mechanize? Well, I'll go through these fairly quickly because I think individually, I won't read them all out, you can just get a sense that you may well be chasing a bug, you may want to change the appearance of code, you may want to standardize use of variables. These are, of course, particular issues if you've got a large number of contributors. And so on and so forth. Or this one, for example, has recently become very important, that we have put a lot of effort into mechanizing the generation of interfaces to the same underlying, reliable, proven code, but making it more modern in appearance, more usable by people depending on what particular environment they happen to want to adopt. So plenty of reasons. Well, okay, if you accept that, well then why all this emphasis on mechanization? Well, NAG in a sense is a special case, that it has lots of contributors and lots of platforms and so forth. You might say, well, I'm a single user, I have one program, what's all the fuss about? I don't need software tools. And maybe you do, maybe you don't. But even with a single program, and I can speak from personal experience, it's surprising how the life cycle of that program is longer and more varied than you ever anticipated. I'm sure some of you had the same experience. You find that other colleagues, to your surprise, it never was your intention, adopt your program and then adapt it. And computers go to the graveyard, new computers come in, and you find the program gets ported to machines in ways that you never really anticipated. So, in a sense, NAG has had that problem writ large, problems of variant control, standardization, testing, documentation, as Brian has mentioned. And so, in our case, it's pretty clear that if you can mechanize, and you try wherever possible to do that, the benefits are very pronounced. Economy, there are potentially huge savings in programming effort once you get the mechanization working. It may take you longer first time round to get the mechanization in place, but once it works, computers are very willing, electrons don't wear out, basically, people do. And it's much more consistent. If a software tool makes a mangle of a program, generally it makes a real visible mangle, which you then can undo and retry. Whereas to do things by hand, and particularly to repeat them, is very tedious and error-prone. And as we've begun to appreciate more and more lately, once you've mechanized, you can then get smart. You can produce different variants of the same code. And hopefully, if you establish certain properties of the original code, the transformations preserve those properties. You hope. But, as you will well anticipate, mechanization is a non-trivial effort, and that's why not many software organizations go to the lengths that NAG has. And a little bit more about that later. Okay, a very brief history of software tools. They emerged in the 1970s, NAG and other groups. What were the driving factors? Well, this was the heyday of the great expansion of scientific computing, mainframes coming to universities, computer center directors, of whom I'm sure there are several in this audience, were the kings of the day. It was the boom time for scientific computing. And Brian's experience at Nottingham, I'm sure, in some ways was replicated, the clamour for reliable software. The emergence of various software groups. NAG, although as a company, was probably one of the first software cooperatives, but didn't realise what it was. We didn't use the term, but that's probably what we were. There were other companies such as IMSL in the States. There were major organisations that had internal software resources, such as Bell Labs. And there were government-funded, particularly US government-funded software activities, most notably the Argon projects that Brian's already mentioned. So there was a community of people interested in addressing the kind of problems that Brian mentioned. Portability, reuse, documentation, variant control and testing. All of those are critically important. Fail on any of those, then the library bombs, your reputation goes out of the window, you've lost your business. Now, I don't know what the language background of this audience is. I can guess that it's some smattering of Fortran, but quite a lot of other languages too. This tool's effort was largely Fortran focused because that happened to be the dominant language of scientific computing. It emerged in that way in the 1970s, but actually the whole issue of software tools is not wholly Fortran based. So I'm going to go through very quickly just a few. Let me just deal with these two. Polish was an example of a Fortran editor. More than just a pretty printer, it actually did more standardization than that, but it was a very useful, popular one. PFort was developed by people at Bell. because they had the same kind of language dialect problems that we had. They produced a sort of restricted dialect of Fortran to help ensure that you stayed within this portable subspace. Now, this is an interesting one, RAT4, Rational Fortran. Some of you may have heard of it, but it's disappeared, essentially. Its aim was to make Fortran a better programming language. Now, there may be people in this audience who say that's a hopeless cause, and you may well be right, but you want to make it more readable, more structured, and it provided better cosmetics for Fortran, lacking from the Fortran standard at the time. What's happened really is that, I remember going to workshops in the 1970s where these kind of preprocessors were all the rage, and we diverted some of our effort into them. Most of that's fallen by the wayside because as modern, quote-unquote, modern features have been added to Fortran, the use of such preprocessors, which critics call linguistic props for deficiencies in the Fortran of the day, as these features have been added, the use of such preprocessors has declined. So you don't hear that much about them these days. But a couple of other quick examples. Branch analyzers, these are very important for ensuring the effectiveness of testing regimes. You want to make sure that control is passed through certain passages of code. That's what this branch analyzer did. Tamper, I put 1973 question mark. For all I know, there's somebody somewhere in an office in the world still working on this effort, which was to a grammar-based transformational system investigating, and still investigating for all I know, mechanized ways of transforming and formatting programs. It did actually have some practical applications in NumPy and in producing theorem-proving software. ToolPack, it was a US project, probably the first organized project of its kind, multi-site, funded in the US, but also involving NAG, and it developed a consistent suite. It was probably the first organized attempt to produce a consistent set of interacting tools with common analysis components and so forth. And it led to 2 public domain releases via NAG, and then later to a commercial tool suite, which is still available via NAG. Okay, so let's come up to modern times now. Primary focus of software tools activity in the 1970s and 80s were on these individual Fortran programming support tools, which to some extent, one has to say, were designed to overcome the deficiencies of Fortran. There have been tools efforts in other languages, and some of you may be familiar with lint for C, for example. But more recently, the general attention in the community, as it were, has been on providing a broader support for the software development and management process. And I've got a couple of examples. CVS, I'm sure some of you are familiar with that. We have adopted that for quite a number of years now, and that is the core of our version control system. We have slight refinements to the standard system, but it's very helpful. You know, it's a great pity that wasn't available 30 years ago. It would have been damned useful then. It is still useful now. Another one that you may be aware of is RIB, repository in a box. This basically helps you if you get code from some source by network. You then change your code, but in the meantime, the original has been updated. So is your change of the update the same as the update of the change? Not always, is the answer. And RIB is meant to help with that sort of thing. And portable software development environments such as Eclipse. Whoops. Last point, in some sense, is the most crucial. There is, as I'm sure many of you are very familiar, more familiar than me, there is a very wide and still expanding family of XML tools, extensible markup language, for describing and manipulating structured information. And as you'll see, that's come to play an incredibly important role in the innards of the NAG library engine or machine. So software tools used by NAG. It really was, as Brian's indicated, I think already, a period of major development in numerical software for all of us, not just NAG, many other groups. We were learning at a pace, and the world of computing kept changing under our feet. New machines were introduced, new standards, new languages, you name it. common aim of NAG and all these other groups was this El Dorado or utopia or whatever of high quality but portable software. So it was as reliable as you could make it was fast as you could reasonably make it, but it was widely available. Had to be widely available. That was the challenge, and we don't claim optimality in either respect, but we're seeking, really are, that has been, if I can use the phrase the Holy Grail, high quality portable software. Now, NAG, in a sense, was a bit of a special case because we had this large, and I don't mean it disparagingly, this large irregular army of people. You can perhaps impose certain standards if you have a set of programmers within one company. You might be able to discipline them in a certain way. We didn't have that kind of discipline. This had to be essentially voluntary adherence to standards, collaboration between all these people and a growing number of full-time staff. We did make our own attempts in various areas. For example, master library file system. We attempted to build one. I think the design was probably okay, but the computing resources available at the time were simply not adequate to cope. So it was as we've come across more than one instance of an idea, in a sense, ahead of its time. From the outset, though, as Brian has emphasized, we were striving at all times to impose standards, ideally which can be checked and enforced mechanically. Strongly influenced, we have to acknowledge the general encouragement and the guidance given by people like Lloyd Fosdick and Lee Osterwald at Boulder, and colleagues at Argonne and Bell too and other places. So in the 1970s, essentially, we were realizing the need for software tools for specific analytical and transformation purposes. And where we couldn't find an external tool, we then began to develop our own, using the most rudimentary text editors initially, whatever we could lay our hands on. We didn't know anything about compilers, compiler writing, and the like. So we really were learning on the job. So we wrote tools like DEX, which made sure that all the declarative parts of programs were properly organized and so on and so forth. But, as Brian's indicated, we had a growing awareness of the role of these software tools within this overall framework, the library machine. And we did make initial forays into computerized documentation, computerized typesetting. We tried to develop a form that could be typeset if you wished, but displayed online on character-oriented terminals. VT100s, I'm sure you remember those. And that was a hell of a challenge, which we partially solved, never fully. But I think this is one instance of trying to automate too early. We used TSSD, which is a very sophisticated program from Harwell ahead of its time, but essentially didn't lead anywhere. And I can now say, in hindsight, we jumped too soon. We tried to go computerize that documentation too early. Okay. In the 1980s, let me put all that at once. You can read as we go through. Because of our experience, we got involved in Toolpack. NAG was the coordinator of that project, even though it was US funded. I think that's probably the first time that's ever happened. We produced a set of Fortran tools that we made available for public domain initially. And we also used those tools internally, and that meant we kept refining the tools. A new standard came along, Fortran 8X, later Fortran 90, and the tool set that was originally Toolpack eventually emerged as a commercial product, NAGware, made available by NAG. And we do, to this day, continue to make heavy internal use. The key thing about this second generation of tools, first time round you make all the mistakes under the sun. Second time round you realize how you should have done it, you make it a more modular design and so forth. And in particular, there were common components for program analysis, the lexical phase, syntactical phase, and this was done in a very open architecture, so you can get at all these bits. And that's crucial for the analytical tools and the transformational tools. Now, the complexity of those tool components were comparable with that of a compiler. So the question was posed, well, why not build a compiler from these components? And as far as we know, it's the first time that question's been posed that way around. Maybe you know better, but I think it's probably true. One of our colleagues, Malcolm Cohen, took up this challenge. I think he probably posed the question, which some pundits said at the time simply wasn't feasible. And within a year or more, he had a working component-based compiler for the then Fortran standard available for internal use. And within 2 years, there was a releasable product. And in our view, that's a truly outstanding feat of programming. And within the realms of NAG work, Brian and I have seen a large number of remarkable feats of programming by some very bright people. This, I think we would say, ranks at least first equal with any of them. Quite remarkable. And Malcolm is still with us. He's very interested in natural languages as well as computer languages. He likes Japanese and old Icelandic. He's currently on not sabbatical. He's seconded to our Japan office. So into the 1990s, the world's first Fortran 90 compiler was released in 1991, along with other NAGWare programming support tools, with the key analysis components in common. That suite has been further developed, both for internal use and external distribution. And the 1990s, I think, were characterized by a growing awareness on our part that we could at last begin to draw together in a mechanized way software and documentation. Essentially, there had been two separate worlds, and it relied solely on the vigilance of the human being to relate that body of documentation over here with this body of software over there. On the scale that we were doing things and what we would like to do with the code, that sole reliance on human vigilance was not adequate. And the really good thing about the 1990s as opposed to the 1970s when we embarked on all of this was that by then there were a number of generally available, very useful information engineering tools. XML, HTML, and the extensible stylesheet language, XSLT. And we were busy, whilst producing regular marks of the library, we were busily engaged in experimenting with such tools, investigating how to manufacture mechanically different interfaces to NAG software for different packages, such as reduce, axiom, and so forth. So, where we are at present, NAGWare developments have continued. The compiler is now at release 5. It has some elements of the latest Fortran standard in it, so it's probably the world lead in that sense, and it's still regarded as the most thorough of the Fortran compilers available. And we've seen more and more emphasis on this mechanization and on the generation of efficient, variable, flexible variants of the library. And with a certain amount of effort, we're now capable of the mechanical production of library software interfaces for different packages, whatever we may choose, within reason. And this, as you might imagine, is a crucial ability for our, in terms of meeting the needs of modern audiences and giving those audiences access to the latest functionality. And that we have, in the style of the library machine, we call this inner core, this inner mechanized core, the library engine. And the motivation, I think we've covered well enough already. There is continuing demand for our library software, but it's being used in more and more different environments, the environments of the day, be they .NET, MATLAB, Maple, whatever. But if we were to try to produce all these versions explicitly and maintain them, the burden would be quite unsustainable. So mechanization is essential. Therefore, we've developed a framework for looking after this. And this is a fairly simple schematic that essentially the library engine consists of the core numerical software. There are various mechanisms that support interface generation, and at the bottom there are these basic linear algebra subprograms and other utilities and the machine constants that Brian's mentioned. So this mechanism is in production use within NAG. Its first major rollout was with Mark 7 of our C library, and then later at Mark 8. So we had a chance to compare the mechanical route versus the previous route, which was, Shanks's fingers basically, manually intensive. At those 2 marks, over 600 fully documented, fully tested, blah, 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 new routines were added. So it was a very, very substantial increase in functionality in that library. The algorithmic components were transformed into C using that same NAGware technology I mentioned earlier. So this is another instance of reuse. That because we've got compiler-based technology, we can use that as a transformational tool. The transform code is not very pretty. We may, in the internals, we make no bones about that, but we believe the internals of these codes are not for public viewing. It's a little like expecting, if you get a washing machine, you expect to have a wiring diagram in which you can tinker or whatever. However, the interface is natural C style using NAG C structs and enumerated types. The error messages are in a C style. So what the user sees looks like a C library. Likewise, the documentation from a generic HTML form is in a C style generated using XSLT, the extensible style sheet language, from XML-based documentation and wrappers. So I'll just deal with this very briefly. Here is the engine. There are the basic components. There are frequent consistency checks run between the base and the specifications in XML. When we want to generate a particular library instance, in this case the C library, the base components are transformed by a version of our own NAG Fortran compiler technology. And using XSLT, the extensible style language transformer, we produce both user documentation. I think this little pointer has done its job. Into the documentation and engine wrappers. The wrappers give a C-style interface to the software, and the documentation also is in C-style. Okay. This technology really comes into its own when we look to the future, what we call connector products. There are, as you well know, some very well-established computational packages. In a sense, these are our great rivals, but actually, we can live with them. We can make use of them, because if we can provide a reliable, efficient, affordable interface with documentation in the native style, then Maple users can become NAG users once removed. MATLAB users can become NAG users once removed, and so forth. And that indeed is essentially where we are at present. So there will be a full MATLAB connector toolbox available shortly, all mechanically generated. Whoops. Yeah. So, okay. Just to summarize, scientific computing, as you will well know, has changed hugely in the last 30 years. I mean, computing has changed. Is it all for the better? Well, we could argue about that. But an element of consistency, and I think one of the great factors about NAG is that we focused on numerical mathematics, and the mathematics is very enduring, shall I say. And so we've been able to focus on algorithmic software, and that's been a common underpin, providing quality and stability. For NAG, the development of new software tools has been vital, and in particular the engine has really been critical for our, not only for our past activities, but for our future success in a changing world. We're pretty proud of what we've done. We've learnt a lot, and we're still learning. We are somewhat disappointed that the take-up of those software tools and the software tools methodology has not been as great in the community as a whole, and that's for various reasons. So that's, I think, where I'll leave this. We have put much more effort, I think, than we ever expected into the realm of software engineering, but the benefits have paid off. Okay. Oops, no. I'll skip that if you don't mind. And that. Oh, okay, one more. Right, what's going to happen in the future? Well, we are firmly committed to develop this software tools approach, the associated engine framework. As you all know, the world continues to change under our feet. There are new Fortran standards afoot, believe it or not. It's the language that refuses to die. Yeah. And so the nature of the requirements will change. There are some signs. I mean, I ended on a slightly pessimistic note on the previous slide that we regret that the take-up has not been as great as we thought. There are some signs among software developing organizations, communities, and funding agencies that the value of having organized bodies of softwares, or library by another name, and what follows from that is if you are going to have widely used and long-lasting, useful libraries, those libraries need coding standards, and our experience, gained the hard way, is that you need mechanization to impose the standards. So that's it. Oops. Any questions? Or?
I'm interested in your attitude to pruning. You mentioned that you thought the old Fortran didn't have control structures, and now you've got control structures. Do you use those control structures? Floating point used to come in all sorts of shapes and forms, and now it's pretty well standardised.
Yes.
You also mentioned that you added some more routines lately, which surely aren't available in older versions of the library. So, can you still produce old libraries, or
no.
how do you prune
No.
those?
We are very conscious of a kind of responsibility to the user community, so that if, for example, if we're going to withdraw functionality, we always give notice of intention to withdraw, that we don't change an interface to an existing routine. We introduce a new routine with a changed interface and so forth. In complete contrast to other software organizations like Microsoft, who play fast and loose with specifications. Basically, we track a policy that balances continuity with evolution. So the internals of the modern NAG Fortran library are actually Fortran 77 plus some Fortran 90 constructs. Internally, we know all the compilers that we now deal with can handle those Fortran 90 constructs. So we've quietly upgraded the body of the code because we know in practice the only likely compilers we're going to deal with in the real world will have those constructs. But we can still express the high-level interface either as Fortran 77 or Fortran 90. So in that sense, we're still consistent with our Fortran 77 users, but we've uprated the body over time. Yeah. But it's a good question. If you insist too rigidly on backwards compatibility, you never develop.
Presumably you get some performance improvements by pruning out the floating point or whatever it is that have got in it.
Indeed, yeah. Oops, sorry.
When we started in the flush of youth, we had no idea what we were letting ourselves into. And we were driven by a recognised need, the need of our users. We didn't have a vision or a desire to build an organisation. And what we were doing was at the cutting edge and technically very demanding. And it needed substantial human and computing resources. We needed numerical mathematics, the algorithm design, understanding of computers and computing languages, software development, and much more. But the fundamental factor was people. Not only people with the required abilities and knowledge, but with shared aims. People who were willing to cooperate and trust one another, who were willing to make a commitment, who'd bring energy to the activity, and then have pride in their work. And this was vital to building the library and to building NAG, and indeed in our ongoing business. And we've been fortunate in having throughout a critical mass of colleagues, both full-time and voluntary, of the right calibre and commitment. And so we had Leslie and Jim and Joan Walsh and Linda and Shirley, Eric Foxley, who was a lovely director at Nottingham, and Alan Scott in Oxford, and David and Richard, Peter Kemp, Laurie Schoenfelder, Brian Smith, and then Jonathan, our solicitor, I'll say something about him in a moment, and James, Ken Broadley, Ian Gladwell, and Dick Jenks, and many others. We also had some wonderful advisors, Stu Feldman, Volvo Gahan from Berkeley, Jim Coney from Argonne, and Alan Scowcroft, who's helped us enormously in the financial markets. And all the contributors, obviously numerical analysis and numerical mathematics, computational statistics, many of them were genuinely world figures. And we're lucky enough to have hundreds of contributors of that kind. And the validators, who genuinely put quality before friendship. And the people who assembled the code as well. And then the implementers on so many different computing configurations. Remember, before networks, everybody had to sit on the machines that the work was done on. And then the distributors, the people who created the library tapes and then distributed them. And of course we had the people who maintained the basic codes and material in Oxford. And of course we had our own dedicated hard-working staff full-time. Steve and I have always tried to lead from the front, and our colleagues had a similar spirit. And so in the list here you'll see the names of Jeremy Ducrow, who brought a beautiful English to our manuals, Sven Hammerling, Mike Hooper, a person who worked hard at the innards, Jeff Morgan, a very good computational statistician, Stuart Andrews, who leads BSNI, Mike Dewar, our current CTO team, CTO man, the sales team. Have you ever tried managing a sales team? It comes as a terrible shock the first time you try and do it. John Zurowski was one of them. Then Carol and Brian Smith, who were NAG Inc. and Haruka and Hiro I mentioned. And Zohair, one of the most caring colleagues we have. Mick Pont, a great, what's the word I'm looking for? An Isaiah amongst men when it comes to numerical standards. And then the current lead team, Susan Shaler, Ian Reid, and Robert Meyer. And then of course we had people like Joseph Wisniewski, a man who was born to farm as a count in Poland, but finished up doing numerical mathematics in Copenhagen. And many others. We jump-started as an informal association in Nottingham in May 1970, and we created a social organisation just to do the job. We had a NAG executive to steer the project, and the Library Contents Committee to design and build the library. And all the founding members, remember, had other full-time jobs. And we were lucky that they decided to call the activity the Nottingham Algorithms Group, and it was coordinated from Nottingham. And the staff were employed in the Cripps Computing Centre under the delightful Eric Foxley. Steve was our first full-time employee in 1971. And I can remember now as yesterday, in December 1972, the Deputy Registrar of the University and the Deputy Bursar saying, "We have come on behalf of our masters. If you go back to the maths department and forget this stupid NAG thing, we promise not to ruin your career." Well, we moved to Oxford the following August at the invitation of Leslie Fox and Alan Scott and that wonderful shadowy thing, the General Board. The General Board still exists through all the reviews in Oxford. There were just three of us. We became the Numerical Algorithms Group, and then Richard Field visited us from the Computer Board, and soon we had an enlarged NAG Central Office funded by the Computer Board through Oxford, and it grew in the university there. And soon we had a powerful library, and overseas universities, large industrial companies like ICI and Rolls-Royce and Shell and government departments were wanting it. But there are alarming issues of indemnity for the university. So we needed a legal corporate status with limited liability to be able to negotiate and agree contracts, and to be able to continue with all of the voluntary collaboration that we had and the relationships. And remember, people were giving us and have continued to give us their IP. And above all, we needed to start earning a living as a fundamental drive. The company needed to make money to sustain itself, and so we could employ our own staff. So after careful review, we decided to become a not-for-profit company, limited by guarantee, associated with, but not part of, the University of Oxford. And of course, at that time, no one had heard of such a body. Well, there were pros and cons, and there briefly, well, those are the things I've told you we needed. So these are the pros and cons to not-for-profit status. We kept away from the venture capitalists, and we've never had to be concerned about what our share value was and move under those sorts of forces. We've received the IP from everyone. They gave it to us because we're not for profit. We've also been protected from takeover attempts, of which there have been several, because we need the agreement of all the members. We'll come to members in a moment. The cons, well, we never addressed the issue of the capital base for the foundation of the company. We've often been short of resources, financial and otherwise, for new products, setting up subsidiaries, for marketing strategies. And at times when the cash flow was difficult and there's a lack of capital resources, the bank became very wary. But they did give us resources for setting up a subsidiary, for example. You probably never thought you'd see this. This is a talk about a software company. I want to draw attention to the value of having good advice, and our particular friend Jonathan Alley, who incorporated the company, wrote our software license, and did so much else for us. Fred Truslove, our auditor, was a great help too, and Philip, one of the partners of PwC, and the early bank managers. So we needed to get up to a living. Oh, there's a story I want to tell you about Jonathan. I think it's a reasonably good one. So we're negotiating with the Ministry of Defence at St George's Court, and I'm small, and Jonathan's even smaller. We go into this great room at St George's Court. There's a huge table. And at the end there are 5 men sitting, and one of them sits there and says, "We're very big, and you're very small, and you'll sign this contract." Well, we'd expected that. So Jonathan and I stood up. Jonathan said, "Sir, I represent the University of Oxford. You're very young." And we began to walk out, and we negotiated a contract. Well, the funding from the computer board stopped on the 1st of August 1978. We had experts in Fortran and working on new systems, and DEC created a new scientific workstation, the DEC VAX VMS 11780. We were the first people to use it outside DEC. And I described it in an email to the people at Digital as an implementer's dream. So suddenly I'm in advertising, and I'm speaking at the DEC user conference at the downtown Hilton in San Francisco. Well, after my talk, I got into the lift at the ground floor. Went up to the 3rd floor, the commercial floor. Lift opens. In gets Sammy Davis Jr. Stands next to me. Door closes. Go up to the 6th floor, the convention floor. Doors open. In come 4 people. The person opposite Sammy Davis Jr. turned and said, "Aren't you Brian Ford? Will you sound my program for me?" Lift goes up to the 7th floor, 8th floor where they get out, 4 of them. As I'm getting out on the 12th floor, Sammy Davis Jr. turns to me and says, "Ain't fame great?" Well, we implemented the library widely. We've talked about that. in numerous numerous programming languages. We've talked about that, and we enlarged the product family. Steve's going to say even a little bit more about that, I think, shortly. Major sources of funding for our research and development was collaborative research. And we became quite good at it. Looking at ideas behind problem-solving environments, algorithms for various forms of parallel computing, visualization in application areas. I've been very tempted to write to the Guinness Book of Records and ask if there's anybody else in the UK who's actually got more than 130 million euros that way. Some lovely moments came from that. Finished up examining a Spanish PhD, and also speaking at Albert Prat's memorial occasion soon after his death in the Politècnica de Catalonia. And having told the assembled audience, I was told it would be 50, turned out to be 700 people. Told them about Albert's virtues. I said, no one is perfect. Albert admitted to supporting Barcelona, and the place exploded. I tell the story because being there and that comment actually captures the spirit of the collaborations we're involved with. We had some wonderful wine and food as well. We had subsidiaries, we needed subsidiaries to get into the markets in US, Germany and Japan. So we started a subsidiary in Chicago in May 1978 in the bedroom of Carol and Brian Smith. The spare bedroom, I should say, not their actual bedroom. Brian was the person who did IcePack. And this wasn't far from Hague National Laboratory. And Chicago became our North American home. But we never truly broke the hold of IMSL on the US market. But we had a great time. I also finished up going on a trade mission, a US trade mission, for supercomputers to Japan, and became the international representative on US government supercomputing policy forums. And this enabled entry into the big labs, Livermore, Los Alamos, Oak Ridge, and places like AT&T Murray Hill and IBM Yorktown Heights. The trade mission also seeded the idea of an office in Japan. But this became effective because of the energy of Haruko Kanjo, who was at the time an employee of SGI, and the language skills of her colleague Hiro Chiba, who's currently our CEO in Japan. And this initiative was funded by a loan from the Midland Bank. And you were pleased to know that both subsidiaries became profit-making and actually greatly aided technical collaboration. I know organisation is not actually a riveting topic, particularly this late in the afternoon, but it's obviously vital if a company is to thrive and grow. Overall responsibility for NAG rested with its executive directors, Steve and I, overseen with great care within our not-for-profit company by our Council of Management. And this effective body oversaw NAG for 30 years. The largest group on the council were elected by the members. Well, who are the members? The concept of member was purposely came into form with the formation of the council, and the recognition again of NAG's corporate nature. NAG was a collaboration. The idea of a NAG member reflected this, and I'm glad to say continues to do so. Our chairmen have always been more than figureheads. I hope you can see them all. The esteemed beauties on the right. Each of them has taken a vigorous and lively interest in the company, and each had their own profound knowledge and involvement in scientific computing, and ways of relating to Steve and me. The position was purely voluntary, and it's good to have the opportunity to publicly thank Joan and David and Richard for all they've done for the company. We've always had excellent people, and invariably they've had several roles. So, for example, Peter Kemp trained as a numerical analyst at Cambridge under David, but has become a senior university administrator. And Peter and I travelled to Chicago together tens of times. And my abiding memory with Peter is having fought our way through the masses at Heathrow, and eventually having got to the desk, the booking agent saying, "Well, sir, that's your wife's passport, where's yours?" But Peter was still in Chicago the next day for the board meeting. And then there's Laurie Schoenfelder, him of special function fame. Laurie has one great weakness. He's an Australian. We had a wonderful game of cricket on a bicentennial cricket match at Argon. And we were on the point of tying. We'd arranged it. When this beautiful strain goes to the wicket and hits a 6 off the last ball and destroys the whole thing. No, I mentioned Ken Brogley here. No one dared to play golf with Ken because he was too good. We had a technical policy committee as well. Learning and talking, sharp it was really. Just people by really highly knowledgeable characters. We come back to one of David's favourites again. Nick McLaren from Cambridge. Nick was so pessimistic that the axes of performance had to be reset when he spoke. So when he said something was absolutely impossible, that translated to achievable with difficulty. And then we had Stu Feldman, wonderful one-liners. Stu's actually the president of ACM, now works for Google. He created the make command in Unix after working with us in Oxford. We're one of the major footnotes there. And then there's Brian Smith, another maniac, who gave up his bedroom. I've already talked about that. He's still a member of the NAG board. His idea of retirement is writing a major Fortran program test harness and walking his dog, Bess, up to the top of the 10,000-foot local mountain each morning to get exercise. So we owe so much to so many. But I'll finish with Jim. This is Jim lecturing at Argon in 1973. And I'm sure all of you will recognise the picture in the top right-hand corner. This is Pilot Ace, which I believe is still downstairs in the Science Museum. Now, Jim always liked drinking and partying. And one day at the famous Numerical Library Algebra Summer School at Ann Arbor, Michigan, Olga Towski, the great mathematician, was having senior German academic visitors to lunch with John Todd, her husband. And Jim often got a little bit lively at lunchtime. So Olga said, "Jim, I understand that beer can come in smaller measures. Have you ever thought?" "Yes, I know, Olga, but it's never been my ambition to use one." Well, we're so grateful for his generous ambitions with us. And I leave you with a slide of the biggest mistake I remember, looking at the whales, sorting out why the Russian rockets weren't getting close to their satellites, by sorting out the best of 6 arithmetic, solving that problem for them. And dear old Malcolm Cohn again. I don't know if you've got any comments or questions.
Could I say, as chairman of the Fortran Specialist Group, how grateful we are to NAG for their support of the standardisation process, including, you mentioned Laurie and Malcolm.
And Brian. Brian Smith has been on the panel
Yeah,
too.
well, I'm fairly new to this thing, so it's, I just wanted to take the opportunity while you're here to say thank you very much for your support, or continuing support. Because Malcolm's still very much support.
That's right. And he, we're involved with standards for reasons I hope we've explained. and it's meant, therefore, it's been very important to us to have rigorous international standards where we can for all the work we're doing. and I believe generally it's worked. Please.
That first line there's answered what was going to be my question to you in a way. Whatever happened to the Ada library? I suppose in consolation, that did contribute to your potential Guinness Book of Records entry. And didn't you and I get a lot of subsidised steaks from the basement of the Berlimont building when we went to all those meetings?
Did we all? Yes, when I saw you earlier on, I was running through, working out where we met. Yes, I mean, I also remember a meeting of the Ada committee where all of you had eaten the same shellfish one night, and the next morning, out of 26, only 2 of us were there. We were only there because we were chairman and secretary.
I seem to remember that you got discouragement from your chairman from pursuing.
Once or twice.
on more than one occasion, certainly, and probably on more than one topic as well, actually.
Yeah, there's the other one, yeah.
Both beginning with A. Yeah.
Both of you,
Yeah. Okay. So you've shown very commendable patience and persistence so far. So I'm going to keep this fairly quick, just to run through very quickly products and services. I hope in a way this ties together quite a few things that we've touched on before. So talking about the NAG Library and the language perspective, which we've just been discussing, in the beginning there was the NAG Library, but really, was it library or libraries? I think it's fair to say that we always had the notion of a single algorithmic source. But the reality of whether there were different language versions of the library and how closely those different language versions related to each other actually has been a long-running issue of major resource importance to NAG. I think the reality is that in terms of distinct language products, the answer has to be plural. There were NAG libraries. And as you've heard, there are a number of marks or editions produced, with Algol 60 being the lead language at first, but then the influence of Fortran grew during the 70s. And we meant various shades of Fortran, but obviously we have experts in that area in the audience, Fortran 4, Fortran 66, Fortran 77, Fortran 90, and so on. And the Algol 60 version fell by the wayside, shall we say. I think late 70s, early 80s, I can't quite remember exactly when. Use began to decline. Crucially, the vendors stopped producing compilers. That's the critical thing. And indeed, at various times, from mid-late 70s until the early 1990s, there have been major NAG efforts to produce other language versions. Algol 68, that was a very serious effort, particularly with Malvern, RSRE, experts there, Ada and Pascal.
There are still strike aircraft flying with Algol 68.
Is that a good thing or a bad thing? It has been a very major factor in the life of NAG. What language should its library or libraries be implemented in? And you can't go into these things lightly. That if you embark, and particularly if you didn't have the full panoply of technology that we now have, it was a very major commitment of effort. And the effort you committed in that direction probably meant you could not add as much functionality or give any given periods. It really was a very, very, very important critical decision. One very significant step was the first release of the C language version in 1991, and at that point that really was a distinct linguistic effort from the Fortran library. But as I've explained earlier, through successive releases, in a sense the Fortran and C library now have a much closer common source and a mechanical path of derivation. And the Fortran 90 language version in the mid-90s too. Okay. So, when we say our software has been implemented on PCs to supercomputers, we really do mean it. This has not been an exercise in vanity on our part, it's been an exercise in necessity. That if we want our libraries used at Lawrence Livermore and wherever, CERN and so forth, we had to have the library available on these supercomputers, even if the strict commercial case didn't justify the effort involved. And particularly in the early days, there was a lot of coding intervention needed to produce, say, a Cray library. And the point is that if you keep updating the base library, you have to repeat those actions every time you update the base. So a huge amount of work and effort's gone into servicing that spectrum of machines. And of course now, well, since the early 2000s, 64-bit systems are becoming the norm, and multi-core systems are also, I mean, PCs we have are typically multi-core these days. Okay. We do have two libraries for high-performance computing. First is the SMP library, the Shared Memory PAL, symmetric multiprocessors, should I say. In effect, this is a tuned version of the Fortran library, and we anticipate that in due course, this library will, as multi-core systems propagate, this library will become the norm, and that the single processor library will become a kind of maintained deviant derivation, should I say. Parallel library is somewhat different, a bit of a standalone library using message passing paradigms. Okay, now we have had very substantial involvement with other packages too. Is that me? I'm not sure. I don't think it is, but I'll put that there and try not to move too far. Particularly statistical packages, and most notably GLIM and GenStat. GenStat particularly is alive and well and now under the care of VSNI, a jointly owned subsidiary between ourselves and Rothamsted. GLIM and GenStat were both groundbreakers in their day, for sure. And other products too, including PDE Solver, for example. NAG Software Tools Compiler is still part of the current range. We had a substantial, I was going to call it flirtation, but I think that underestimates, substantial engagement, consummation with Axiom, an algebraic, a computer algebra package, a very, very sophisticated package. This was developed by IBM during the 1990s. We mentioned briefly, I think, graphics library. In its day, that was a groundbreaker, but a portable graphical library in its subroutine form. An RS Explorer, an advanced visualization system, which is still part of our product range. Now, why did we, in the 1990s, have this product range expansion? Well, essentially, I think there were two reasons. The first was that lots of knowledgeable people within and on the periphery of NAG were concerned about the long-term future of subroutine libraries. They really felt, they wondered if they had any kind of future. Now, in hindsight, we can say they were wrong, but that was a very powerful advice we got. The second reason was, you might say, more to do with technical vanity, or we had this vision of an advanced, well-populated, well-interconnected scientific computing environment in which there was some sort of application layer, either written by package developers or written by users using compilers and programming in the traditional sense, a kind of variegated middleware consisting of all sorts of components, numerical algorithms, statistical algorithms, symbolic components, visualization interface and so forth, and basic components. We had a sense of that, that's the way the world should go, and I think it's, in the 1990s, we had a product range that potentially covered all those bases, after fashion. And in that sense, I think we can be reasonably proud of what we did, that as a technical feat of absorbing technology from these other parties, IBM in one case, Rothamsted in another, Silicon Graphics in a third, we took that all on board and we made sense of it. We absorbed it and we adapted it, and we could make this component speak to that component. But I can say, after the event, that it did lead to substantial overstretch of effort. And it was at a time of increasing competition, both from the public domain. The US government continued to fund mathematical software library development. IBM transformed the visualization market by declaring its visualization product, Data Explorer, to be open source. Overnight, that transformed the market conditions for scientific visualization. And in each of these areas, other than the libraries, we were essentially competing against better resource rivals. Our staff in any given sector, be it symbolic computing or statistical computing, were fighting against the odds, against the bigger, better resource rival. Actually, we had quite a bit of success in doing that. I think we more than held our own, but I think essentially we were boxing above our weight. I would say that in hindsight now, just too overstretched. And the doomsayers about the future of the library turned out to be wrong, just as well. And as you all know, in computing itself, in the late 1990s, early 2000s, essentially the kind of ever-expanding universe of computing burst. The dot-com bubble, year 2000 preoccupations, which didn't necessarily affect us too directly, but certainly affected computer budgets, and those affect our sales. And the whole world of computing continues to change, and sustaining, carrying that mass of complex technology forward was just not sustainable. So we have essentially gone back to basics. We focus now on libraries. Okay.
I'll have to find a voice.
We focus on Fortran, C, and S&P libraries, and I think in a way we can now go back to saying the NAG library is singular. We've almost got back to singularity. The current edition of Fortran library is Mark 21, so Brian talked about producing a mark of the NAG library every year. Well, we've redefined the concept of a year. We now have a NAG year, which is about 17.2 months or something like that. 21 marks over 30-some years. But if you consider all the other things we've done in the interim, the Ada library, the Alpha 60 library, this package, that package, not done too badly. And that has over 1,400 user-callable components. Next mark is due later this year, and somewhere in the region of 100 routines. And some of those are fairly mundane algorithmic stuff, but one or two very timely, overdue additions like global optimization, wavelets, and so forth. That figure's wrong. 50 plus should be 70 plus. That's my time for mistake for the day. One of them anyway. And also currently available Iris Explorer and the NAG Web Compiler. And this is an area of increasing focus, as we mentioned before, connector products that make our algorithmic software available to relevant third-party products. MATLAB, Excel's been available for some time. Okay, moving swiftly on. Now, for the first 20 years or so, NAG was an entirely product-based company, and we made a certain reputation. We certainly gained a lot of expertise the hard way, experience the hard way, gained contacts, and that we led us to begin to offer technical services from sometime in the 1990s. Services to computer manufacturers, end-user consulting, or, and this is increasingly important, licensing our technology to other software developers. So if we can't compete with them directly, we can ride with them. They can gain competitive advantage by using our components and package and so forth. And that's, just to give you an idea, that's about a fifth of our business, or until recently it's been about a fifth of the business. A major development in the service side has been the awarding of a contract under Hector. I suspect most of you know broadly what Hector is. It's the latest generation UK computing support, UK research supercomputer facility. And NAG's role is to put to use some of that expertise mentioned above to help scientific researchers port their applications to this new system and to make those ported programs work effectively. So, looking to the future,
probably agree, NAG is unusual. Some people may say weird or whatever. It is in some ways different from a lot of other software houses, but in one respect we are just the same as any other trading company. We survive if and only if we're profitable, particularly since we don't have backers. What's therefore very crucial is that we keep our eyes and ears open, we understand how our markets are evolving. We've actually not talked a great deal about users in this presentation, perhaps we should have done more on that, and that we continue to invest. One of the pros, as Brian mentioned, of being not-for-profit is that if we make surpluses we can reinvest, which we do. There has been a significant market shift over the years. The primary market sectors in the past were academic, industrial, government, probably something like 45%, 30%, and the rest 20%, something like that. Predominantly academic, major industrial companies like Philips and manufacturing companies. But interestingly now, if we rank our two top market sectors, it's academic and financial. That may or may not come as something of a surprise to some of you. The finance market is very important to us now. There's increasing use of financial mathematics. There's an emphasis on quality and reliability that is not adequately addressed by the public domain software. And therefore there's a particular niche for a quality software provider, often in keeping with other packaged solutions as well, to use it for comparison purposes. And indeed the financial sector is now well over 20% of our business and is by some distance the fastest growing. Okay, so this is basically saying we're not sure what's going to happen, but the good news from our point of view is actually the use of numerical components is growing all the time. More and more practices, more and more industries, more and more sectors of government, you name it, are using analytical techniques, or using computing models for the sake of their work. And in that sense, we are part of an expansion, we're well placed. So what we have to do is to continue to offer expanding functionality. We make sure, for example, that new components added at Mark 22 will be of particular interest to the financial sector, but not exclusively. And this emphasis on quality continues to be essential, especially in that market. And we also anticipate that Connector Library is going to keep the library available to more accessible to wider markets. And in due course, we think that the experience that we're gaining by providing the Hector service is likely to influence the future shape of our high-performance computing products and services.
Well, obviously the building of the library with similar ventures has led to the design of these scalable algorithms and the portable numerical software. And we've recognised already the profound impact this has had on world science and engineering and other areas of human endeavour as well. And the importance that the sums has in all of these things. We started a centre for computational finance in Oxford, and just before he was appointed had the Governor of the Bank of England come, and it was absolute magic. He said, the trouble is, we can't get enough numerical mathematicians. That was the first time we'd ever heard that. Well, but thanks to the efforts and skills and commitments of many people, we're now well into our fourth decade. We must be one of the older software companies in the UK. We've obviously had some setbacks, but a number of successes too. Because the whole thing is evident all the time. It comes down to people. So thank you very much for inviting us to tell you about the NAG Library story. You may find it difficult to believe that we've actually had to be quite selective in what we've said this afternoon. And it's been suggested we ought to write a book about it. Thank you for staying the course. And if there are any questions or comments as we finish, we'll try and answer them. Thank you very much.
Right.
Please.
Have you attempted to make a relationship with Microsoft?
Yes, we actually had at one point a contract with them for a statistical library. Microsoft created, I think it was 128 projects. And the idea was that if they got those 128 products with what they had already, they would totally dominate the market. But they're actually stopped from doing it by the US Department of Commerce, which is quite interesting, isn't it? So they did have that thought. I guess now we have to try and make a relationship with Google.
I should say, Brian, that we actually do now have a consulting contract with Microsoft, which is not so much to develop statistical software, but to check the statistical software they have. So this is very commendable that I'm not sure how much it's, yeah. They want to make sure that their statistical software, particularly as used in Excel, is highly reliable, and so they've turned to us for helping them play.
There's that wonderful work done at NPL by Maurice Cox and others of his colleagues that pointed out the inadequacy in the Excel spreadsheets and the extensions that were being sold. I think this caused a lot of people to ask questions because obviously the spreadsheets are used so extensively.
Thank you.
Please.
You put up a number of 1,000 or so customers. Have you never considered making it available to the likes of myself at a price that I could afford?
There are all sorts of things we failed to do. One of the things, for example, we let numerical recipes get into the market. But we decided that we actually couldn't do books like that effectively. I'm no longer directly involved with the company. The thing was riddled with my personality, and very reasonably they decided that was enough. So I've had to step right away. But Steve's still actively involved. And I'm sure that's a very good question to ask, because it's the kernels that people want for their computing, but it is comparatively expensive. So as a potential user, Steve, I'd commend that suggestion to you.
It is a very pertinent question, the whole business of licensing. The library inherently is a collective product, that it appeals to, in the era of centralized computing resources, you had a collective product that was available to a large audience. What you're talking about is adapting to the new age where personal distributed computing, and we have been looking at personalized licenses, not least so that if a researcher moves from one university to another, he can take under license a relevant portion of the NAG library. So it may come, but it's not there yet.
Please.
You mentioned you had a graphics library. Is that sort of part of the package, or is it?
Well, the two areas there. Well, first of all, Christian Reich was asked by F.L. Bauer to create a graphics library for the Leibniz Rechenzentrum in Munich, and from that we were given the portable codes that Christian had developed, and then Ken Broadley developed those, and they're still very extensively used actually, simply because of the sheer quality of them. We've then spent a lot of time and effort in visualization. Ken's still involved on the board of the company. I'm not sure, Steve, what the current state of the work in visualization is.
Well, the graphics library is still on the product shelf, but it's not promoted. I mean, we're not in a position to develop it, and because we're not in a position to develop it, we don't promote it. But it is still in use, and it's supported. So if we get bug queries, we track them down.
Because when I used to work, we used the simple plot.
Yes.
For
Yeah.
bus, but of course, unfortunately, they've gone bust.
Yeah.
And we're now in a situation where we're changing computers, and the simple plot version that we were supplied with no longer works. Right. So,
Well,
that's
do
the
have a
sort of
word with
problem-
that.
That's the sort of
I mean,
problems that you have
do
to
get in touch
face.
with us. I can give you a card or a contact. We may be able to help. I mean, we, as I said, we don't promote the library anymore, the graphics library anymore, but it continues in use for those sites who want
I
to
know
use it.
Simpleplot is used,
Yeah.
particularly across government departments. I wonder what their problems are going to be when they change computer systems.
We had the experience in early years of discovering that another well-known graphic system was actually arranging its curves, for example, for aircraft wing design, by eye, which is horrifying. And the good thing about the work that Christian and Ken did, it had very specific mathematical properties, so that you knew you could define the graph that was being given against specific norms.
As the chairman, since my name has been taken in vain so many times by our speakers, I intend to wrap up and conclude by just saying one or two of my perspective of NAG. And I think it goes like this: that NAG has two unusual features. First of all, it's actually concerned with quality rather than bad quality. If you look at most computing and most products, they're distinguished by their lack of quality. Operating systems, language compilers, they're shoddy, frankly. But NAG, because it's involved with numerical computation, has to be high quality to make any sense at all, and to get the right answers. They mentioned earlier a particular product called Axiom, which was battling. It was a perfect product, like all their products, even though it came from IBM. And it was battling against a popular product, which we will name nameless, which was very pretty. It was a beautiful product. Everyone loved it. But I was told by my colleagues, yes, but it gets the wrong answers. Now, when it comes to numerical work and computation, it matters, and that's what NAG does, and very few people do otherwise do. So that's the first unusual feature of NAG. The second unusual feature of NAG is not for profit, it's commercial status. Unlike most spin-outs from universities, Brian and his colleagues did not go to make themselves fortunes. They were concerned with the quality and remained producing the products. Steve said a moment ago, you have to make copies to live, well, you have to actually make money to live, and you don't fall into profits. And again, that is unusual in our business. And you can argue for a long time whether it's a good thing or not. But the fact that they've been successful in both makes them unique. And so I think they've done a marvelous job. Thank you very much, both of you, for coming today. See some of you again on the 17th.